Hello. Now we will calculate the moment of inertia for a linear object, which is a rod, about the axis which is perpendicular to the rod but passing through one of its corner. So this is my axis. So the motion will be happening like this. So axis will be passing through one of the corner like here. Okay. So mass of the rod is given m and the length of the rod is given L. So to calculate the moment of inertia, first we have to divide this rod into the elements. Okay. So for that, what we will do, we'll move perpendicular to axis along the rod and we'll go for x distance, general point basically. When we are cutting the element, we have to go for general point. Okay, so after moving to a general point, we make a cut. So this cut is dividing this rod into two parts. Okay, so after this cut, we move further by a distance dx. So obviously this dx and the x, they should be in the same direction. Okay, whenever we are making a cut. So after moving dx, we make one more cut. So between these two cuts, I am getting my element and the mass of the element I am taking as dm because this is very small. Okay. So we get dm, we get the element. Now we have to calculate the dm in terms of the given quantities. For that, we have to define the linear density. So linear density lambda. So I'm assuming here linear density to be uniform because nothing is given. So if something is given, we have to take that linear density. But since nothing is given, I'm defining the linear density to be uniform. So if it is if linear density is uniform, in that case, lambda, which will be defined by lambda, will be equals to m by L. That is equation 1. So mass divided by area. Mass divided by length is defined as the linear density. So after defining the linear density, we have to calculate the dm mass and which will be equals to linear density multiplied with the length of the element which is dx. So let's put the values. So m by L dx becomes mass of the element, equation 2. This has become mass of our element. Okay. So this element, if you see, this is a point element. And now we want to calculate the moment of inertia of this point element about the given axis, which is perpendicular to the rod and passing through one of the corner. I'm calling it O. So moment of inertia for a point mass is defined by this formula, I is equals to mr square. This is the moment of inertia for the point mass, where m is mass of that point, and r is the distance of the point with respect to the axis, perpendicular distance of the point with respect to the axis. R is perpendicular distance of the point with respect to the axis. So you see here that perpendicular distance is x. So now we can use the formula. So the moment of inertia for the element, I am calling it DIO. For the element will be, if we use the formula, will be equals to mass of the element, which is dm, multiplied with r square, where r is a perpendicular distance of the element with respect to axis, which in this case is x, so it will be x square. Okay, so let's replace the values. Let's put the value of dm here. So DIO will be equals to m by L x square dx. This is my equation 3. So this becomes the moment of inertia for my element. Okay. Now we have to calculate the moment of inertia of the rod. So we have to integrate this thing. So let's integrate. So we'll integrate the moment of inertia of the element in such a manner so that the whole body should be covered. This is a sign for that. So we'll put the values. M by L we will take out of the sign of integration because this does not depend upon the variable, which is a x in this case. X square dx. And we have to put the limits basically so that the whole body should be covered once. And limits will be put for the variable which is a x. So we'll be putting the value of x starting and final so that the whole body should be covered. If you can see, if I keep cutting the element starting from x0 to xl, x is equals to L, I'll be covering the whole body. So lower limit will be 0 and the upper limit will be L. So if I change the value of x from 0 to L, I'll be covering the whole body once. And that's what we want. So now let's integrate that. So if I integrate x square dx, the value is going to be x cubed by 3 from 0 to L. So now we have to put the limits here. So it is m by L. First we will put the upper limit. So that will be L cubed by 3. We'll replace the x by the upper limit. That is L. So it will become L cube and 3 is already there. Minus 0 because lower limit is 0. If we take this out, it will be m by L multiplied with L cube by 3. And if you write the total value, this I naught is going to be mL square by 3. So this becomes the moment of inertia for this rod about the axis which is perpendicular and passing through the one of the corner. Okay. Now if you can see this formula is different than the formula when we had the axis which was passing through the center of mass. So you see, that proves our point. If you change the axis keeping the rod same, the moment of inertia is going to change. So whenever we define the moment of inertia, it is defined corresponding to axis along with the object. So there is two aspects to the moment of inertia. One is the object and second is the axis. Orientation, relative orientation, everything. If you are changing that, the moment of inertia for the same body will change. So this thing you can memorize. This is the moment of inertia for the linear rod about the axis which is perpendicular to the rod and passing through one of the corner. The moment of inertia will be mL square by 3. Okay. In this case, we have taken one assumption. So you have to always memorize that. And that assumption is linear density is constant. So if nothing is given regarding the linear density in the question, you will always assume it to be uniform. But if they give you the linear density as a function of something, like as a function of x, you have to take that linear density and then you have to solve this whole equation following the same process. Process will remain same. And you might get the different formula in that case. You will get the different formula in that case. Okay. So that's it. Thank you.